Hello, welcome again. We are solving some conventional questions of power plant. Our topic is gas turbine. Question number 47 from Civil Services Main 2014-15 is a gas turbine operating on actual simple Brayton cycle is to be designed for maximum output. If the maximum and minimum temperature of the cycle, the efficiencies of compressor and turbine are fixed, drive the expression for optimum actual pressure ratio. What will be the value of optimum pressure ratio for turbine if the ratio of maximum and minimum temperature is 3 and gamma is equal to 2? Take efficiencies of turbine and compressor as zero point 0.9 and zero point 0.8 respectively. So here this is your gas turbine cycle with process 1 2 dash as actual process in compressor and 3 4 dash as actual process in turbine. Isentropic processes in turbine and compressor are 1 2 and 3 4 respectively. 2 dash to 3 is your heat addition and 4 dash to 1 is heat rejection. T3 is the maximum temperature, T1 is the minimum temperature, and isentropic efficiency and compressor efficiency of the turbine and turbine are constant. So this is these two quantity and these two quantity are constant. Okay. So now work done by the work done is net work done is given by CP T3 minus T4 dash and C minus this is compressor work, this is turbine work, and CP T2 dash minus T1 is compressor work. So this is turbine work, this is compressor work. So now these are the actual temperature difference T3 minus T4 dash. Converting it into isentropic temperature difference, that is T3 minus T4 multiplied by isentropic efficiency is your T3 minus T4 dash. So T3 minus T4 dash can be written as isentropic efficiency of turbine into T3 minus T4, and similarly as the compressor requires more work than isentropic work, so T2 dash minus T1 can be written as T2 minus T1 divided by isentropic efficiency of compressor. Okay. So now we can take Cp and T1 as common. So W by Cp by T1 is equal to isentropic efficiency of turbine T3 by T1 minus T4 by T1. Okay, taking Cp and T1 as common, and minus 1 by compressor efficiency T2 by T1 and minus 1. Okay, now T3 by T1 is a constant quantity because T3 is constant, T1 is constant. So taking it as small t and multiplying and dividing here T4 and T1 by T3 and T3. Okay, or multiplying this term by T3 and dividing this term by T3. So now T3 by T1 is T, and T4 by T3 is ratio of temperature drop across turbine, and this is equal to R raised per gamma minus 1 by gamma, where R is pressure ratio. Okay, and similarly T2 by T1 is R gamma raised per gamma minus 1 by gamma, and T3 by T1 is small t. So this so we can take T as common, and isentropic efficiency is 1 minus 1 by T3 by T4 can be written as R gamma minus 1 by gamma, and here we can write it as R gamma minus 1 by gamma minus 1. So now putting R raised by gamma minus 1 by gamma as x. Okay, so now the equation will be WCP by T1 T isentropic efficiency of turbine 1 minus 1 by x minus 1 by C x minus 1. Okay, now this is Cp and T1 are constant. This is also constant. This is also constant, and compressor efficiency is also constant. So, but W is variable. So, differentiating this with respect to x, because x is variable, x is function of R, and CPT1 are constant and W is variable. So it means W by CPT1 is varying with x. So differentiating this W by CPT1 respect to x, we get its differentiation is 0, and its differentiation is minus 1 by x, differentiation is 1 by x square, and its differentiation is 1. So x square will be your T isentropic efficiency and compressor efficiency. So X is root T isentropic efficiency and compressor efficiency, and X is R raised to power gamma minus 1 by gamma. Okay. So now we can put the values given. So T is given as 3, gamma is given as 2, isentropic efficiency is given as turbine is given as 0.9, and for compressor it is 0.8. So R comes as 2.13.